switch gears and tell what library is present in um, Python. I'm not going to discuss now the one which you have in your manual, but I got to discuss a couple of stuff which could help you. So with that introduction, I'll just switch to one of the small library program which I have written here. So hopefully you're able to see my screen. Yes. Okay. So basically, this is a small library program. It's not your program. This is a sklearn tree, which is present in the decision tree, which is present in a sklearn package and things like that. Now this was not even a program. I'm just using this small snippet to explain a couple of concepts. Okay, and please don't use this anywhere because it wouldn't yield anything for you. It's just for me, it is just for my reference. Now, um, so what am I doing here? I have downloaded from somewhere the CSV file, the diabetes.csv file, and pretty much you see this one is it consists of a continuous variable, which means it could we have to define the buckets for it rather than it coming with bucketized stuff. And then what I'm doing is I'm splitting that particular data. I mean, I'm reading that CSV file onto the memory, which is what this line does. And then I'm splitting that particular data into training set and test set. Okay. Now the thing with this particular thing is I'm giving the test size. Test size is point. It could go from anywhere from 0 to 1, which means a 1 corresponds to 100% and 0 corresponds to 0%. And I'm also giving some random states. So how much of randomization I should be using it over here. Then I am instantiating an object of decision tree classifier, and I'm giving the criterion as entropy because that is what ID3 uses, entropy or information gain. Like I already said, information entropy is the measure of impurity, whereas information gain is a measure of how much information it is giving. So it's kind of inversely proportional. Um, and so I can use other criterions, Poissons, or I can also use Gini index. Most of the criterions are present in that particular class. It's open source again. Go ahead and try to explore it. You should be able to see lots of people writing the code to that. Then what I basically do is I'll construct the model. So by giving the training set, and then I will use the model to test the test set, or I'll predict the test set. And then what I basically do is I'll be printing the accuracy. So what is this accuracy? Accuracy score, there are various ways to, there are various ways to talk about accuracy scores, but in just the accuracy score is, hey, I have y test which consists of the actual classes which has been defined versus what is my model predicting here. And it says what is a percentage, what is a percentage of accuracy I have. Okay, and this set of lines I just lifted it off from somewhere, where it says, what are the, just draw the graph for me. That's what it means. Now, so I want to introduce you to a couple of things here. Test size. It plays a very important role for us. Okay, and what should be my training size versus test size given a particular data? And I want to just show how much of accuracy are we expecting, or how much it happens, and all of those. Let me just keep the maximum depth of 3 here first. Okay, so it was 100 because I was trying something, and then I'm just going to run this. And then, okay, as you can see, it's about 70% accurate. Okay, and let me also make the random state as 1 as it was before. So let's see, did it successfully run? Okay, so I mean, just by here, by reducing the randomization, samples to 1, and the depth of the tree being 3 levels, I was able to get an accuracy of 7. That's a 7% increase in accuracy, as opposed to randomization of 1. And hey, what does the tree really looks like? I took the liberty to place it on the desktop. The tree really looks like this. See, depth of 3, the tree with the depth of 3, and I believe the black node is what it means the root node is, and clearly, you know, there is a lot of entropy here. I mean, if you see the entropies at the leaf level, right? The leaf level entropies for some of them are pretty high. For example, if I am taking extreme left, it's 0.863, and one of the entropy over here is 0.976, and clearly the depth whatever I'm choosing is not that great, right? Because I see a lot of impurity even though we have reached the decision. Okay, but on the other hand, the accuracy has increased. I'll come to in some time I'll tell you why that could be a case. Okay, now let's modify the depth to something higher. Let me close this so I don't get a file handle problem. So let me choose the depth to something which is bigger. I can put 400, but I'm just choosing 40, or I can put a 400. That's fine, and then I'll run this. I mean, if you see, I'll touch upon a bit about it came back to 70%. Now that is fine from 77. I'll talk about a theory or hypothesis, but the accuracy fell down to 70% again. Now let's look into what my tree looks like right now with a depth of 400. You see, this is my tree. It is way complex, way spread out, okay, way pinpointed, should I say. Now let's zoom this in, and then I don't know if you're able to look at all the zooms one. You see, sorry, let me try to. You see, I mean, the entropy is pretty much zero. That means the impurity is pretty much zero here. I think on all of the leaf levels, if you take a look at it, or subleaf levels, the entropy is almost zero. All of the leaf levels. That means it is it is accurate to or the from the training data's perspective, the impurity is zero. When it reaches to that means it is very much certain that this is the class which it has to be. Now, how well it performed in test data, that's what I'm looking at the accuracy, which actually fell down to 70% here. Okay, now let's put something optimal, 15 or 16, not as big as 400. How am I choosing the depth number? Just random. Oops, I'm going to definitely encounter file problem. So let's take a look at this tree again. Hopefully it was able to write successfully. Was it? I don't believe so. It did. Hold the file handle. I didn't write it doesn't nicely. Okay. Now, as you can see, there is a little bit of increase in the accuracy from the test data, but it is still there. Okay, so this one is still, you know, too too much pinpointing. Now, now that said, I can reduce it to more, probably 10. You can probably have it in a loop and try to build a graph out of it as to how much am I trying to, or what is the what increases the accuracy versus, I mean, the moment I decrease the max depth to 10 years, so the accuracy increased by 3 more percent, which is good. And my tree, how did it perform with the training data? It kind of changed, but it spread across, right? Now let's stop playing around with the depth and start playing around with the type of training data and test data, right? Now let me change something here. Let me change my test size to 90%. That means my training size is 10% of the overall data versus the test size is 90% of the um, you know samples whatever I have. And let's take a look how what happens over there. Accuracy is fine, I mean 71%, but you see the tree how it is built. This is the tree. Okay, and if you really look at it, it's totally unbalanced, because you see there is some, this tree is pretty larger. The tree on the right, I mean, this is not pretty intuitive tree here. I mean, if you really take a look at it, this is my left part of the tree and this is my right part of the tree. It is pretty huge. It is not balanced, unbalanced tree, not pretty good. Okay, so it's not pretty much balanced, and it is spread out on the right side. So really, if you look at it, I think the test size does matter. Okay, so let's say I take 50% training sample, 50% test sample. Okay, now the accuracy fell down by 1%. I mean, it went below 70%. But okay, let's see how my tree is built. Okay, so kind of balanced tree. I wouldn't say totally balanced, but mostly it's okay. But here and there, I see an entropy which is 0.98, which is a lot of, which is a lot of impurity up there. So, and over here as well, 0.918, lot of impurity. So what am I trying to convince you guys here is that, okay, the depth of the tree is one of the factor. The size of the size of training data and test data matters over here, and the amount of randomness matters more as well. So let's say, for example, let me close this and run it. I chose some random data again, as opposed to 1%, but I chose more random data. Then my accuracy kind of increased to 73%. And my tree should be looking probably more balanced, or maybe not. My left tree is more heavy than compared to right tree, I think. So various factors matter on how the tree is built, whether um, whether this model is the right model or not. So with introduction, I just want to stop presenting for a bit here and then switch back to my um, explanation on whiteboard kind of presentation. Oops, sorry, that's my son who did something. Okay. Okay. So now I've explained to you multiple things which could affect, you know, um, which could affect, the training tests and how to define training set and test set and sort of those. Now let's see what is the induction bias on a decision tree. Now, I hope you understand the meaning of what is a bias and a variant. Do you? I mean, have they learned what's a bias and a variant? Trade-off?
No, sir. No, sir.
They haven't learned.
No, they haven't.
They haven't. Okay. So let me just slight bit introduce you to the concept of what is a bias and a variance. Okay. So a bias means, hopefully I'm able to write it. Give me 1 second. Okay. So there are two things which you want to learn: a bias and a variance. Okay. A bias is, let's say, let's take the example of classification itself. And in the example of classification, um, you know, uh, and let's say I have two classes, 0 and 1. Let's just, for simplicity's sake, take binary, no, binary classification. Now, if the model I prepare is biased towards or towards leaning towards a particular class in any of these two, then that is considered as high bias, right? It's as simple. I'm trying to build a model and I want my model to be biased low. Okay, as much less assumptions as possible and as much less biased as possible. That means it should have it should be a generic model and not weigh on one side or the other. Okay, so that's a bias. And a variance, on the other hand, hey, it depends on the type of data which I use. That means, let's say if the data is targeting a particular class, okay, if data is targeting a particular class, then that is, that is, I'm sorry, let me take that back. That is a bias. A variance is something which is estimate, if the training data is spread out too much among both the classes. Let's say if I take a 50-50% of of both, then it is considered to have equal variance or low variance, as opposed to if the data is lying more, is lying all around. If let's say, for example, if I have a multi-bucket um, thing and the data is lying all around in the domain, then that is something which is considered as a variant one. So um, and the bias and variance trade-off is something like, an algorithm should have low bias and low variance. That means it should not lean towards a particular class, and it should try to fit all kinds of data which it has. Okay, so that is what is a bias means. Now, in this, we specifically talk about induction bias or inductive bias. Okay, and in machine learning, more specifically, we try to talk about what is mean by inductive bias. And this term of induction is, again, we brought it from, uh, information theory, and I did briefly mention about Shannon's information theory. Um, Induction, in other words, is generalization, right? So if I build a model using any of the algorithms, my model should have low bias, which means it should not lean towards a particular class. Low variance. That means it should handle all kinds of datas and all kind of surprises. That what let's put it that way. And it should be general model. That means it should not be for a specific training data set or a specific test set. It should be a general model. Even when we are designing something, we ask people to design in a way where all other people or all other customers also can use it. So similar way, a model should be not to a specific set of data which we have, but it should be to us, it should be generic one. Okay, which means it should perform well even if we start seeing a new trend of data. Okay, and the term inductive bias, okay, is the term inductive bias, which we use quite constantly, is a set of assumptions we make in order to achieve generalization. Okay, in order to achieve this concept of generalization, while even writing the algorithm, we we tend to make some assumptions, and those set of assumptions are called as inductive biasing. Okay, now any clarifications until now? What is a bias? What's a variance? My thing should be a low bias and low variant. And what's a inductive bias? And any questions at all? Okay, so let's okay. So now let's get back to the decision tree, inductive biasing of the decision tree, right? So we tend to say that the decision tree um, with smaller size are easy to interpret and easy to even look at. Okay, easy to look at, easy to let's say easy to execute, doesn't occupy more space, and takes less time. Okay, as opposed to a larger tree which I showed you, they occupies more space but will be more specific or will tend to have a higher bias. Okay, and as I said, the with respect to the subtrees, right, I mean, it could have more specific or subtrees which are repeating itself could be there. So these are couple of bias problems which we have with respect to decision trees or with respect to our algorithms ID3 and the other algorithms. Now there is something called which is called as an which we term it as Occam's razor. I Okay, and this Occam's razor, what they say is simplest hypothesis fits the data. Fits the data. Now, what does this mean? So a simple thing which I showed you in the classifier, I was able to attain 77% of accuracy when the tree depth was about 5. When the tree depth was about 5, irrespective how it is performing in the training data, but when the tree depth reached, you know, um, about 5, and with samples of about 90% to 10%, 90% training data to 10% of test data, I was able to receive about 77% of accuracy when it comes to um, when it comes to test data. Okay, so which comes to the discussion of what is underfitting and overfitting. What is the meaning of underfitting and overfitting? So an underfitting, a model which works bad in both training and test set, is termed as an underfitting. Okay, and a model which works good in training set but bad in test set is an overfit model. And why does either model overfitting or underfitting occurs at the first place, right? So let's talk a bit about what is model overfitting, and then we'll go to underfitting. Overfitting generally happens for one of the reasons, like presence of lot of noise, okay, lot of bad data, okay, can have can lead to overfitting. So one of the things for overfitting is bad data. Okay, multiple data or multiple data of the same same attributes having the same values and all of those multiple data. Lack of representative samples, lack of samples um, in training data. So like I said, when I was choosing the sample data, when I reduce the set to point one, which is 10%, and versus on the training set I reduced it to 90%, I was able to show that it had its own problems. Like the accuracy went really low, it went beyond 69%, right? So lack of representative samples could also lead to sometimes underfitting. So it falls into both buckets of underfitting and overfitting, but this is mostly the probability. Okay, and so these are some of the things which you know which you will face with respect to overfitting, and with respect, these are some of the problems which could lead to overfitting of the data. So I'll take a small pause just to see if you have any clarifications about what is overfitting and underfitting. Okay, now let's talk a bit about how can we how can we reduce the problem of underfitting and overfitting with a thing called, which is pruning. Okay, pruning simply means stop constructing the tree, or stop constructing, or either stop constructing or don't consider a part of tree. Which means, like, say if you have a tree like this, okay, it's a big tree, and let's say in this particular subtree, if I don't have a representative sample, I will prune these two and say, hey, this one just has one node. This node will be representative of rest of the tree below it. Okay, so that is what simply pruning means. Okay, so there are two kinds of pruning, or there could be multiple kinds of prunings, but there are specifically two things which we use: pre pruning and post pruning. What is pre pruning and post pruning is at each level when I am trying to build a tree itself. A pre pruning is I'm not trying to, I won't go to the max depth. When I am trying to build a tree, I will see how much of information gain that is giving, and if it is max information gain, then I will not go ahead and further expand the tree, but rather I will slap a class on it and then stop further expanding of that tree itself. That is called pre pruning. Versus post pruning, on the other hand, what happens is I will build the tree to the max depth. I will build the whole tree to the max depth, and then what I will basically do is I will parse the tree again using, there are many methodologies to parse the tree. You can use DFS, breadth first search, or depth first search methodology, and then try to find, hey, this part of the tree is mostly having, a set of information gain, then I don't need the rest part of the tree, or it is this particular node is representative of everything below it. So I'm going to just cut the tree at that point and then just give it to you. Okay, this is one of the ways of pruning. And the other way, which hey, we just saw, is considering the depth of the tree. Hey, I just want my tree to go to the depth of 10, max depth of 10. That's it. If slap a tree when it is reached, slap a label on it, with whatever, with whatever the maximum information gain class we have, and then I want to stop at that particular depth alone. So these are a couple of types of pruning which we have. Okay. Now this is mostly about, there is one other concept which I want to handle in decision tree itself, is continuous values. Okay, continuous values and converting it into, kind of discretization with respect to that is, is that, let's say if I have, in your, I think there is a Platonist thing which you have, right? I mean, if I introduce the attribute of temperature, which has like, hey, 20 degree, 22 degree, 24 degree, 28 degree, and play to be yes, no, no, yes. So hey, how do I divide this particular continuous variable into discrete buckets? Because that is what, that is what it takes a tree to say, hey, if it is less than something or if it is greater than something, right? So I can, well, this again uses the concept of entropy and information gain, but I can say, hey, if it is less than 22 or greater than or equal to 22, then just go towards it. Okay, so this is some way of, and we will also use this calculation of information gain and things like that, in calculating in with continuous values as well. So one last thing which I want to use, where exactly decision trees could be used in, in real world examples. And before I go to that, ma'am, do you want me to cover anything else with respect to decision tree, or I'll just go to real world applications and then wrap up?
Yes, sir. That'll be good. Real world applications.
Okay. Okay. So decision trees again. One of the things which we use decision trees for, I can probably talk about it in a very high level. So let's say I'll give you a very high level overview of why I use a decision tree here. Okay, so let's say I we own Windows, right? Uh, what we are, anybody and everybody are customers for us in Microsoft, right? Now, one of the things which we do is one of the things which we want to do, and I have billions of customers, okay, for Windows, right? Now, let's say I have a version V1 of Windows, and I want them to upgrade to version V2 of Windows. Again, I'm being so cautious in using the terminologies because I just want to make sure I don't reveal anything which is confidential. So I have a version V1 of Windows and I want to move them to version V2 of Windows. When I say I want to move them, that means I want to upgrade them. Why do I want to upgrade them? Because it is more secured, more features, and things like that. Now, one of now I have these billion machines, okay, and this billion machines comes with various attributes, various CPU capabilities, right? Various memory capability. It can extend anyways from 1 GB to, I don't know, 256 GB or even more, right? Of memory, um, hard drive capacity, uptime, which means how much of how much of people are using. I mean, it could lead from anywhere from 1 or 2 minutes to all 24 hours a day, or 24 hours a day and all 365 days a week, 365 days a year, right? So so uptime. So consider these are all attributes. I'm just saying one or two, but I have more than 50, 60 attributes which I build a decision tree off of. Now, based on these attributes, I want to categorize these billion machines and decide whether I will upgrade my machine or any given user machine from version 1 of Windows to version 2 of Windows. Okay, so this is where the decision tree comes handy for me, right? It's a typical two class problem where, hey, upgrade as yes or upgrade as no. It's a typical two class problems, but the challenges come with the number of attributes and the type of attributes which I have. I mean, look at it. I mean, these are attributes. Probably this is bucketized and this is bucketized, but this is continuous for me. Hard disks are continuous, uptime are continuous variables. Now, we in one of my teams have built a machine learning model, which I think we have gathered data for more than 6 or 7 or more than a year, and then we will try to build a ML model or the decision tree model, which gives me whether a given machine is upgradable or not. I'm talking a machine. I'm not doing a machine per day, but in reality, I'm doing so many machines per day. But at least it tells me the set of machines which I want to upgrade or not. So this is one of the real world example which we use, a decision tree on, or we have built a model, and it is not a single model which we have built some ages ago, and leave it at that. I think it handles everything. I think that amount of accuracy or generalization is something which we haven't reached yet. But based on the need of the day, which means if I get some new data, if I get some new attribute which I want to handle, I think I'll have to change the model accordingly. So, and believe me, building this model takes a lot of time. So we have to build an algorithm which is suitable in such a way that if I introduce a new thing, it has to adjust the tree accordingly. Okay, it's not even half an hour or 1 hour. It takes hours to build a model. So So these are couple of you know uh, usefulness which we have with decision trees. And building a complete model is an NP complete problem. If you have concentrated on your algorithms and know what is an NP complete, I think it's quite complex. Okay, so these are some of the practical applications which I know of. I think there are more used in financial domain, especially in financial domain where they have and stock market and things like that, where they have a bunch of attributes to decide whether they got to invest in something or not, or whether they don't want to invest in something or not. So all of these machine learning models or decision tree models are applied over there. Okay, so these are some of the this is decision tree algorithms. I think we have covered it for more than 3 classes now, or 3 classes exactly to be now. Next sessions, I think we will go to another kind of you know supervised learning model, which we call it as artificial neural network. Okay, so before moving on to artificial neural network, any clarifications on decision tree themselves? Any clarifications on how decision tree works and things like that? Yes, no, maybe.
Students, please answer. Sankadeep, Sankadeep, Naveen, any clarifications more required?
Okay, proceeding further. So I just want to spend some time where this artificial neural network came into picture from. I think it's mostly defined from human beings themselves. Okay, where where we have the brain, in any human body we have a brain and a spinal cord, and pretty much everything is human body is taken care by these two, which we call it as central nervous system, right? And this artificial neural network is derived from this concept of brain and the or concepts in which is I can talk a lot about how these two things work, but the major thing with or the major cell which takes care of activities of all of these are the neurons. Those who have had a biology background, a neuron looks something like this, and this is what we and this is what we call it as a cell body. Okay. um, this is a nucleus. This is what we call as a cell body. These are axons. These little things which are coming out of cell body are dendrites, and these are synapse, which could connect with what's below here. What's below the synapse is which could connect with another neuron. It could synapse with another neuron or a muscle fiber. Okay. Now, I'm just going to give you a brief explanation about this, and then I'll leave it at that and take up artificial neural networks and how computer science evolved out of it in the next class. So so there are and so there are two things which you want to know here, and it, which could be useful for us is, given a neuron, it could have inputs from multiple other neurons. Okay, a neuron could have input from multiple other neurons, or some of our own senses which we have, which is an eye, ear, skin, and all of those, which could have input from any of those. Okay, when it says, color vision or something like that, it's again the number of neurons which are firing. I want to specifically introduce you to two things, which is called, rather one thing which is called action potential. There is a resting potential, but action potential is where, and I know because we are all science students, I think we should know what a potential means. And action potential is important because that is what carries your electricity from one neuron to another. Let's leave it at that. I mean, there is a lot of intrinsic details in how an action potential is initiated and how it passes from one neuron to another. I don't want to cover all that, but how an electricity is passed from one neuron to another is what action potential is all about. And um, and there is one important principle here which says neurons that fire wire. Okay, that means a stronger action potential occurs when it gets from multiple sources, or you know um, that means if multiple neurons starts firing and all, then the action potential is much stronger. So you will, all of these concepts which I told you is pretty high level, and I want you to map it to actually how artificial neural networks are built out of this one. With that, I want to conclude today's session. I'll talk more about neurons in the next session as well. Thank you very much. Unless you have any questions, that's it for today's session. I'll just pause for a couple of minutes.
Thank you, sir.
Okay. Thank you very much and have a good rest of the day.
Thank you, sir. Good day to you too.
Thank you.
So Wednesday no classes, no, sir?
Why not?
Yes, sir.
Why not, ma'am? Do we don't want to have a class on Wednesday?
You said you are busy on Wednesday. You will let me know later on.
No, Wednesday. Oh no, I'm so sorry. Let me call you. Thank you.
Yes, yes, yes. Do text me, sir.
Thank you. Thank you.
I'll just inform students. Okay, thank you, sir.
Thank you.
Good day, sir. Bye, sir. Students, you can leave. Thank you.